Mr. Sharma. I hope you're doing well. Today I'll be delving into the fascinating world of mathematics and its practical applications. So for this interview, I chose part A. The first question and the topic was exponential and logarithmic function applications, specifically decoding environmental alert systems. Environmental alert systems are crucial for monitoring pollution levels, which often change exponentially due to various factors like chemical reactions or changes in the environment conditions. So in order to create a question like this on environment, I wanted something that was unique, something that was fun to solve and not just a bunch of numbers. So I came up with the idea of the city of Hamilton using a special algorithm to encode the alert levels for pollution in the city based on the half-life of a hazardous substance released into the atmosphere by nearby factories. The initial concentration that I gave for this substance was 1,000 parts per millimeter, and the half-life is 6 hours. And what I did here was I created a table where I have the alert level range for pollution and the code word. I'm just going to talk about the math behind this. So for part A, it says an alert has been announced. It has been named alert level A. Calculate and decode this alert by answering the following questions. So question number 1 asks us to determine an equation of a function that models the scenario the best. So the equation I chose was c is equal to c of 0 multiplied by half t to the power of t divided by h. Now, the reason why I chose this was because, as the question says, the concentration of this substance typically decreases over time, and this is modeled by an exponential decay equation, which is this equation right here. So c of 0 is 1,000 parts per million, and then t divided by h is 6 hours, which I took from the question, giving me a final equation of c of t is equal to 1,000 multiplied by 0.5 to the power of t divided by 6. Now this equation is very important because it will be used to further solve part B, part C. Without this, we will not be able to solve further. Okay, so I got my final equation here, and I'm going to move on to question number 2, which says calculate the concentration of the substance after 18 hours. So I've been given time, and I know my equation is set for time, right? So c of t is equal to 1,000, we know that. So I can simply sub in t is equal to 18 and calculate, which gave me 125 parts per million. So the concentration of a substance after 18 hours is 125. So this is how the equation just helped us. Okay, moving on to question number 3, it says use the concentration from question 2 to find the alert level A using a logarithmic scale. So we don't know what alert level A is, but we do know the concentration given, so we're going to figure our way out to solving this question. Okay, so in order to encode the alert level A, which we don't know what it is, we're going to use a logarithmic scale. So for this, we need to create a new equation because we have a concentration equation, right? So what I did here was I used a logarithmic transformation of the ratio of the current concentration, which is 125, to the initial concentration, which was 1,000. So I'm going to be using a base 2 logarithm because the decay is modeled by the equation getting in half. Sorry, by the substance being in half. So the log 2 would be best to represent this relation. Also, a fraction of a substance is remaining compared to the initial amount. So this is best represented by c of t divided by 1,000. So this creates a new equation of log 2 multiplied by c of t divided by 1,000. However, the logarithm on its own gives us a positive value when I did the calculations, and this causes it to decrease as t increases. But since c of t decreases, so the concentration is decreasing, adding a negative sign ensures that the concentration of A increases as c of t is decreasing. So this aligns nicely with the alert levels with lower concentration, which indicate greater danger. Multiplying by 2 scales is necessary. So what I did here was I have the new equation, A is equal to negative 2 log 2 multiplied by c of t divided by 1,000. I'm going to be calculating my random alert A, which I don't know what it was. So simply subbing in 125, which I found in my previous question, would give me an answer of 6 here, as you can see. So the alert level A is 6, which was found using the new logarithmic equation. And question number 4 is relating to this question, which is decode this alert level using the table determined in the city's response. So using this table that I have right here, I know that my alert is 6, so 6 to 8, so 4 to 6 would be warning, but 6 to 8 would be danger. So using the table, I found that for pollution 6 to 8, it comes under danger, but since A is equal to 6, it corresponds with the code danger. So what does this help us indicate? It helps us indicate that the city should be acting fast because they are in danger. So this is how this setup has helped us. So moving on to the next question, which the next part of this question, which is part B, calculate for critical level. We're going to determine the time t when the alert level reaches critical. So we don't know exactly at what time we are reaching a level that is not safe for the city at all. What I did was, like, I set an inequality here. So we know it needs to exceed 8. I took my equation that I found in the previous question. A is equal to negative 2 log 2 multiplied by c of t divided by 1,000. And I set that equation greater than 8. That's how I got a number from this calculation after setting the inequality. I'm going to take my concentration equation and I subbed it into that to get exactly at what time I'm reaching a critical level. I took the concentration, I subbed it into 62.5, be less than 62.5, which is a concentration I solved for it, and then I got time is greater than 24 hours. Basically, the time should be greater than 24 hours in order for the city to reach a critical level. Okay, moving on to part C, verify and explain. A technician claims that at t is equal to 12, the alert level should be warning. Verify this claim. Okay, so in order to prove this technician correct or incorrect, we need to solve, right? So we know that time is equal to 12. So we're going to use the initial concentration equation that we found in question number 1 of part A to sub in t as 12. So this is what I did over here. I subbed in c is equal to 12 in my initial equation that I found in part A, and I got 250 parts per million. Now that I have the concentration, I'm going to use the new logarithmic equation that I found to set t is equal to 12 to find my alert. After subbing in the values, I just got 4. So an alert of level 4 corresponds to caution, as you can see. Caution, 2 to 4 is caution. So from the table we found out, so it's not warning. So the technician is basically wrong. This is how we were able to prove it. So this is basically my equation and the thinking behind this whole problem. It's a bit complicated because there's so many steps to follow, but I hope you liked it. Please feel free to reach out to me and ask any questions. Thank you and have a great day.